Hello, this is the lecture PowerPoint for Chapter 16 of the CHANG textbook, Acids and Bases. What we have over here on the left is Alka-Seltzer tablet. And an Alka-Seltzer tablet is used when you have a lot of stomach acid. You will take Alka-Seltzer. Well, if you have a lot of acid, this base will help neutralize your acidic stomach. Over here to the right is some very damaged trees. And what we see from these trees is this is what happens in the presence of acid rain, is that what will happen is these treetops, you'll notice it's starting at the treetops, will exhibit this almost burning or dried out because they had acid, which came from precipitation with acid rain. On slide 2, learning objectives. What we need to know are 3 different definitions for acids and bases. Arrhenius, Bronsted, Lowry, and our Lewis acid definition. We're going to learn about the amphoteric amphiprotic property of water. We're going to evaluate the water ion product constant and relate to pH and pOH. We're going to recognize strong acids and bases. We're going to evaluate the relative strength of acids and bases. We're going to use equilibrium constants to predict pH and percent ionization for our acids and bases. We're going to predict equilibrium concentration for polyprotic acids, relate molecular structure to acid strength, predict acid-base properties of salts, and predict pH effect of oxides in water. On slide 3 then, acids. Well, some of the characteristics of acid are they have a sour taste. When you have vinegar, that has a very sour taste due to the fact that vinegar is made up of acetic acid. Citrus fruits contain citric acid. Acids will react with certain metals to produce hydrogen gas. Acids will react with carbonates and bicarbonates to produce carbon dioxide gas. Characteristics of bases. Well, bases have a bitter taste. Bases feel slippery. Many soaps contain bases. On slide 4, the official Arrhenius acid-base definition says, this is the earliest acid-base definition, which classifies these substances of how they act when they are in water. So an acid is a substance with hydrogen in its formula. And when it dissociates, it will yield hydronium ions, H3O+, versus a base is a substance with hydroxide ions in its formula. And when it dissociates, it will yield hydroxide ions. When an acid reacts with a base, we will undergo neutralization and make water. The delta H for this reaction is minus 55.9 kilojoules. On slide 5, this next definition, so that was Arrhenius. The next definition for an acid is a Bronsted-Lowry acid. Bronsted acid is a proton donor. A Bronsted base is a proton acceptor. So our example here, when you look at NH3 in water, you may be saying, well, they both have hydrogen, so that's why we need this Bronsted-Lowry definition to help us see what happens. What you probably want to do to understand what happens is look what happens with our pairs is that ammonia picked up a hydrogen ion to become the ammonium ion. Water, which we like to write HOH in these reactions, what we can see when we bracket it and see what it turned into on the product side, it turned into that hydroxide ion. Well, what happened is it lost a hydrogen ion. Therefore, according to our Bronsted-Lowry definition then, our acid is our water. It is a proton, and let's remember a proton is really a hydrogen ion. Take the element hydrogen, it has 1 proton and 1 electron. If you strip away its electron, it will just have a proton. And so that's why we call it a proton donor, a hydrogen donor when we have our acid. Now, over on the ammonia then, is going to accept that proton. It's going to accept that proton and move from 3 hydrogens up to 4 hydrogens. Then what will happen on our product side is now it's easy to identify who's the base on the product side, is that it's the hydroxide ion. Finding the acid, let's do the reverse. In the reverse, the ammonia is donating the hydrogen to the hydroxide ion to go back and make water and ammonia. So what we actually say is that by doing these brackets is that water is paired with the hydroxide. Water on the left side is the acid. On the right side, that base, since they go together, it's called a conjugate base. And the base, since we bracketed the ammonia with the ammonium, the base on the left is going to be paired with this conjugate acid over on the right. Please note, you only use the word conjugate on the product side. Acid and base are on the reactant, but conjugate acid, conjugate base are on the product side. Slide 6, example 16.1. Identify the conjugate acid-base pairs in the reaction between ammonia and hydrofluoric acid in aqueous solution. Remembering that a conjugate base always has one fewer hydrogen atom and one more negative charge, or one fewer positive charge than the formula of the corresponding acid. So when we looked at NH3 plus HF, okay, well, NH3 has one fewer hydrogen atom and one fewer positive charge than the NH4. So one fewer hydrogen and one fewer positive charge, plus 1, 0. The fluoride on the product side has one fewer hydrogen atom and one more negative charge than our HF. Therefore, the conjugate acid-base pairs are the ammonia with the ammonium ion, the hydrofluoric acid with the fluoride ion. Continuing our discussion of acid-base properties of water, on slide 8, let's discuss auto-ionization of water. Now, just as the definition shows here, auto-ionization means the self-ionization of water. And what we're looking at with our equation is that water, and let's write it HOH now, is going to dissociate into hydrogen ions and hydroxide ions when you put it in water. So this again is called self or auto ionization, that it does it without any prompting. What happens is technically is this lone pair of electrons on oxygen are going to be donated to a hydrogen, and then this bond, these electrons are going to go back to this other oxygen. When this is the case here, when this is the case, what we get then is the formation of this. This is how we form hydronium ions. We have the lone pair on the oxygen with 3 hydrogens and that +1 charge. Please remember, it's an ion, polyatomic ion, so it belongs in brackets. And then what's left is the OH minus group. So 2 waters will auto-ionize into hydronium ion and our hydroxide ion. Now, the hydronium ion again is H3O+. Now, was it tough to identify the acid on the left or the base? No, it's either one could have been acid or base. However, once you denote who's the acid, you're going to have to realize that the acid is going to have its conjugate base on the product side, and this conjugate base in this case will be the hydroxide ion. If this water is the base, that means it's the hydrogen ion acceptor, then here is the conjugate acid. The hydronium ion would be the conjugate acid on that product side. On slide 9, continuing our discussion of the ion product constant of water, If, again, when water dissociates, we get hydrogen ions and hydroxide ions as our products. How do we write an equilibrium expression for this? Take the concentration of the products raised to the power of their coefficients divided by the concentration of the reactant. Now, in this case, you have water and water. Well, the concentration of water is going to be constant. Therefore, the Kc of water, the equilibrium constant of water, is really known as a Kw. And it's equal to then the hydrogen ion concentration times the hydroxide ion concentration. This is technically called then the ion product constant, Kw, for water, and it's the product of the molar concentrations of the hydrogen and hydronium ion, or hydroxide ions at a particular temperature. At 25 degrees Celsius, Kw is going to be equal to 1 times 10 to the minus 14th, and that should start to bring back all kinds of thoughts about our pH scale and the number 14. But the hydronium ion concentration times hydroxide at 25 Celsius will be 1 times 10 to the minus 14. The assumption is that the hydrogen ion concentration is equal to the hydroxide ion concentration. And so if that's the case, then you will have a neutral solution. However, if you have more hydrogen or hydronium ions than hydroxide, then you should have an acidic solution. If you have the hydroxide ion concentration less than the hydronium ion concentration, then you will have a basic solution. On slide 10, example 16.2, the concentration of hydroxide ions in a certain household ammonia cleaning solution is 0.0025 molar. Calculate the concentration of the hydrogen or hydronium ion. On slide 12, our solution to rearrange equation 16.4, we write in 16.4 again was Kw is equal to the hydronium ion concentration times the hydroxide ion concentration. When we rearrange to solve for the hydrogen ion concentration, we're going to divide both sides by our hydroxide ion concentration. And so we're going to substitute in 1 times 10 to the minus 14 divided by 0.0025. Our answer here then would be 4.0 times 10 to the minus 4th is going to be our hydronium ion or hydrogen ion concentration. Because the hydrogen ion concentration is much less than the hydroxide, then we know this solution is basic, as we would expect from the earlier discussion of the reaction of ammonia with water. On slide 13, now let's take all this and relate it to a very familiar pH scale. So pH, we say, is a measure of the acidity. And pH is equal to mathematically minus the log of the hydrogen ion concentrations. So your solution is neutral if your hydrogen ion concentration is equal to your hydroxide ion concentration. At 25 degrees Celsius, the hydrogen ion concentration is known to be 1 times 10 to the minus 7. Well, if the hydrogen ion is 1 times 10 to the minus 7, the hydroxide ion will also be 1 times 10 to the minus 7. So the pH is going to be equal to 7 at this concentration. How do we know? Put in your calculator, minus the log of 1 times 10 to the minus 7, and you will get a pH of 7. Try that. Make sure you can do this so you will be able to calculate these pHs. Oh, there's a shortcut to this, isn't there? Isn't that all we have to do really is take the inverse of the sign? Careful, only if you have a whole number for a hydrogen or hydronium ion concentration. Your solution is going to be acidic if you have more hydrogen ions than hydroxide. If your hydrogen ion concentration then would be greater than 1 times 10 to the minus 7, therefore your pH would be less than 7. Your pH would be less than 7. A basic solution would have the hydrogen ion concentration much less than the hydroxide ion concentration. If the hydrogen ion concentration is less than 1 times 10 to the minus 7, then the pH is going to be greater than 7. pH will increase as your hydrogen ion concentration decreases. Again, hydrogen ion is going to drive the acidic nature of your solution. A low pH is going to be acidic. So if you have a high pH, meaning as your pH increases, that means you must have less hydrogen ions. On slide 14 then, here's our table 16.1, which has our pHs of some common fluids. Gastric juice in the stomach. If you knew this, that your stomach has very, very acidic conditions. Gastric juice can be 1 to 2 for a pH value. Lemon juice, 2.4. Vinegar is going to be 3.0. The orange juice, 3.5. Urine, depending on various things, is going to range from 4.8 to 7.5. Water exposed to air. What are we saying? We're saying that it will become acidic, and that is because of water being exposed to air. It's going to pick up carbon dioxide, and therefore it's going to become similar to carbonic acid. Now, a lot of people think that blood is neutral. Blood is not. Blood is in that 7 range. Here is a few more acidic thoughts: saliva, milk, and then pure distilled water. But now let's start heading into the basic region for pH greater than 7. Blood again, 7.3 to 7.45. Tears, let's think. Oh, those are going to be in the neighborhood of 7.4. They're somewhat acidic. The milk of magnesia, the base that you use when your stomach has a high acid content or is upset, would be milk of magnesia, pH of 10.6, and household ammonia is 11.5. Your very, very strong bases like sodium hydroxide, depending on their concentration, will get closer to 14. Now here's our pH meter over to the side, and that's what we will use in order to do a few of our labs now. There's other important relationships when we're doing these calculations. We can solve for pOH. That would be, what is the hydroxide ion concentration? Well, if we can solve for a pOH, minus the log of the hydroxide ion concentration is what you'll use in your calculator. When you use a hydrogen and hydroxide ion concentration should equal Kw, which again is 1 times 10 to the minus 14. The log then, pH, you define to be, pH is minus the log of the hydrogen ion concentration. pOH is minus the log of the hydroxide ion concentration. And so both of those numbers should be 14. So pH plus pOH should equal 14. Now that's great when you have nice and easy, even numbered pHs. But as you look at the real world, very few pHs actually have a whole number. So that's why in example 16.3 on slide 15, we're going to have some concentrations that are not whole numbers, whole integers. Hydrogen ion concentration in a bottle of table wine has 3.2 times 10 to the 4th molar right after the cork was removed. Only half the wine was consumed. The other half, after it was standing open to the air for a month, was found to have a hydrogen ion concentration equal to 1 times 10 to the minus 3rd. Calculate the pH of the wine on these 2 occasions. So on slide 16, our strategy, if you're given the hydrogen ion concentration and asked to calculate pH of the solution, what is that definition of pH? Well, according to equation 16.5, pH is equal to minus the log of the hydrogen ion concentration. When the bottle was first opened, 3.2 times 10 to the minus 4th molar was the concentration of hydrogen ions. So when you substitute that into pH is minus the log of hydrogen ion, it's then minus the log of 3.2 times 10 to the minus 4th. Do this in your calculator. Make sure you get the correct answers then. And you should get a pH of 3.49. On the second occasion, we can see this is easy. There was a whole integer there. And so then all you have to do is take the exponent and reverse the sign. And that is your pH. Your pH for 1 times 10 to the minus third is 3. On slide 18, a comment. An increase in hydrogen ion concentration that caused the decrease in pH is largely the result of the conversion of the alcohol, the ethanol, to acetic acid, a reaction that takes place in the presence of molecular oxygen. On slide 19, example 16.4, the pH of rainwater collected at a certain region of northeastern United States on a particular day was 4.82. Calculate the hydrogen ion concentration of the rainwater. So this goes back to our opening slide. This is the effect on our trees when you have this acidic rainwater. It's called acid rain. On slide 20, the strategy. Here we are given the pH of a solution and asked to calculate hydrogen ion concentration. Because pH is equal to minus the log of the hydrogen ion concentration, we can solve for hydrogen ion concentration by taking, technically, the anti-log of pH. That is, H is equal to 10 to the minus pH, as shown in equation 16.6. So on slide 21, pH is equal to minus the log of the hydrogen ion concentration. And again, the problem said that was 4.82. So therefore, take the log of the hydrogen ion concentration is equal to, get rid of the minus sign, move the minus sign over, minus 4.82. To calculate hydrogen ion then, we take the anti-log of minus 4.82. Please do this on your calculator. For most of you, it's going to be that 10 to the x key. So the hydrogen ion concentration is equal to 10 to the minus 4.82. And please see if you get 1.5 times 10 to the minus fifth molar for that concentration of the hydrogen ion. On slide 22, let's check. Because the pH is between 4 and 5, we expect the hydrogen to be between 1 times 10 to the minus fourth and 1 times 10 to the minus fifth molar. Therefore, the answer was reasonable. On slide 23 then, example 16.5, in a sodium hydroxide solution, hydroxide ion is 2.9 times 10 to the minus fourth molar. Now calculate the pH. Our strategy solving this problem takes 2 steps. First, calculate pOH, and then calculate pH of the solution. So pOH is minus the log of the hydroxide ion concentration. Again, try this in your calculator, minus the log of parentheses 2.9 times 10 to the minus fourth, close your parentheses, equal sign, you should get 3.54. Now, on slide 25, we use equation 1610. If pH and pOH equal 14, then solving for pH is going to be equal to 14 minus whatever the pOH is. So 14 minus 3.54 gives us a pH of 10.46. Alternatively, we could use the ion product constant of water, Kw, and that's hydrogen ion times hydroxide ion concentrations to calculate the hydrogen ion concentration. And then we calculate from the hydrogen ion concentration. You can get the pH. You should get the same answer when you do that. Some people don't like to do that because you're working with all those negative exponents. The bottom line is this answer shows the solution is basic, pH is greater than 7, which is consistent with a sodium hydroxide solution. Slide 26. What we need to keep track of is dissociation. If you have a strong electrolyte, like sodium chloride, what happens when you put that in water? It will, way back to chapter 4, blue sheet, purple sheet, it will completely dissociate to give you sodium ions and chloride ions, 1 mole of each, because that's how many we had on the left side. A weak electrolyte, though, will not completely dissociate. This is acetic acid. It really does not want to get rid of that hydrogen. So it will dissociate that hydrogen off, but as quickly as it does, it will reform back to the acetic acid. Now, strong acids Our strong acids are going to be our strong electrolytes, like HCl. Will completely, we want you to keep track of this. The arrow goes completely to the right to give you hydronium ion and chloride ion concentrations. The all the way to the right. Nitric acid. Remember, how do we remember our strong acids? You go to North High School. So nitric, and then we should have our sulfuric for the S, and we have hydrochloric for our H in North High School. These are your strong acids. Now, there's other strong acids. Perchloric acid is strong, and it will, again, completely dissociate to give you those hydronium ions and these anions. On slide 27, though, weak acids are weak electrolytes. HF is a weak acid, and when you put it in water, you will get your hydronium ions and your fluoride ions, but notice the arrows. The arrows go in both directions, meaning as soon as you ionize off this hydrogen, it reforms and will come back to form water. Nitrous acid is also a weak acid. And then that HSO4, after you've lost that first hydrogen ion in sulfuric, this acid is weak. And of course, water is considered to be a weak acid. Strong bases are strong electrolytes. We mentioned sodium hydroxide will be a strong base and completely dissociate into those sodium ions and hydroxide ions in the presence of water. Potassium hydroxide, same thing. So you can see the group 1 and some of the group 2 will be our strong bases. On slide 28, though, our weak bases are fluoride ion reforming into HF. That is going to be a weak, considered a weak base. And again, notice the double arrows, how we will completely reform our back to our reactants. NO2 minus in the presence of water will dissociate to give us our hydroxide ion and HNO2, but again, that's going to be weak. Now, this puts everything, makes everything interesting in an equilibrium constant, these weak acids and bases. So you have to keep track of this fact, is that when you have this conjugate acid-base pair, the conjugate base of the strong acid has no measurable strength. Meaning if you had the strong acid, that conjugate base is going to be considered very, very weak. Hydronium ion is the strongest acid that can exist in an aqueous solution, and the hydroxide ion is the strongest base that exists in an aqueous solution. On slide 29 then, here's table 16.2, the relative strengths of conjugate acid-base pairs. Again, when this strong acid, perchloric acid, loses that hydrogen, you will get the conjugate base, which, as you can see here, is what we consider no measurable strength. Our HCl turns into the chloride ion, hydrochloric acid, and again, these are our strong acids. As you saw, these were the hydrohalogens, except our hydrofluoric acid. That is not a strong acid. But hydrochloric, hydrobromic, hydroiodic are considered strong, as well as sulfuric and nitric. And then that hydronium ion. Here's our list of weak acids. As we go down, and you can see our organic acids, our formic and acetic, are going to be considered weak acids. Now, this is, notice how acid strength increases at this side, and then we would have, with our conjugate base, our strongest base would be down here. We said our hydroxide ion was one of our strongest bases. However, in your organic world, the amide ion is also going to be strong in a strong base. Slide 30 then. Let's look at a strong acid HCl. And here's what you need to peek at over time, is HCl is a strong acid and will completely dissociate into hydrogen ions and chloride ions. And when it does, look how before ionization, all you have is the acid concentration. But at equilibrium, all you have are hydrogen and chloride ions. Okay, hydrogen ions and chloride. So here's the picture here. These are your negatively charged chloride ions being surrounded by the positive, slightly positive ends of water. And we have our hydrogen ions that are going to form our water, is what will happen, and then some hydronium ions. This is what happens with our strong acid. This is very important. You have, at equilibrium, no reactant left, and all you have are going to be your products.
This animation demonstrates the difference between a strong acid, hydrochloric acid, and a weak acid, hydrofluoric acid. Click on one of the buttons to see hydrochloric acid, HCl, or hydrofluoric acid, HF, dissolved in water. Hydrochloric acid is a strong acid. Strong acids are strong electrolytes, which for most purposes are assumed to ionize completely in water. In this case, HCl ionizes completely to hydrogen ions, H+, and chloride ions, Cl- hydrochloric acid donating an H+ to water, producing hydronium ion H3O+, and chloride ion. The role of water in this reaction was not shown to simplify the animation. You can think of H+ as a shorthand representation of H3O+.
When we have a weak acid, like our hydrofluoric acid, this is what, remember, we want, although when hydrofluoric dissociates, you will get your hydrogen ions and your fluoride ion. You will get that two-way arrow. So here, what you see is you have HF still present at equilibrium. You lost some HF, some that went into forming the hydrogen ions, which again would go with the water to form hydronium, and a very few of your fluoride ions. There's the fluoride ion. So what you have at equilibrium is you have to take into consideration at equilibrium the concentration of your reactant and of your products in your equilibrium expression when you have a weak acid or base.
Hydrofluoric acid is a weak acid. Weak acids are weak electrolytes, which only ionize to a limited extent in water. At equilibrium, a hydrofluoric acid solution contains mostly non-ionized acid molecules, HF, and a small amount of hydrogen ions, H+, and the conjugate base ions, F-. This reaction is better represented as hydrofluoric acid donating a proton to water, producing hydronium H3O+, and the fluoride ion. Remember that weak acids only partially ionize in water. The role of water in this reaction was not shown to simplify the animation. You can think of H+ as a shorthand representation of H3O+.
On slide 31 then, calculate the pH of a 1 times 10 to the third molar concentration of HCl and a 0.020 molar barium hydroxide solution. On slide 32 then, the strategy. Keep in mind that HCl is a strong acid and barium hydroxide is a strong base. Therefore, these species completely ionized and no HCl or barium hydroxide will be left in solution. The ionization of HCl is HCl turns into hydrogen ions and chloride ions. On slide 33, example 16.6, now let's look at the concentrations of all the species. The hydrochloric acid, the hydronium ion, and the chloride ion, both before and after ionization. So here's how we do our ICE tables. You're going to have on line 1, just like we did in last chapter, is your reaction. And so what we had was HCl ionizes one-way arrow to the hydronium ion and the chloride ion. Your initial concentration of hydrochloric acid was 1 times 10 to the minus third. Your change, let's go vertically here, your change in that hydrochloric acid concentration is it's going to all be gone. It will completely ionize. So in our change line, put minus 1 times 10 to the minus third. So your final concentration of your acid, a strong acid, is 0. The hydronium ion concentration and chloride ion concentration was 0. Because there's a 1-to-1 mole ratio here of hydrochloric acid to your hydronium ions and your chloride ions, your change line will be plus 1 times 10 to the minus third molar for each of these. The final concentration, you add up these lines vertically and you get 1 times 10 to the minus third for both the hydronium and the chloride ion. The positive change reminder here is that you have an increase in concentration, and the negative change indicates a decrease in concentration. In other words, the reactants are used up and the products are formed. So if the hydronium ion concentration is 1 times 10 to the minus third at equilibrium, then the pH is easy enough to calculate to be 3. On slide 34, part B, barium hydroxide is a strong base. Again, each barium hydroxide unit produces 2 hydroxides and 1 barium ion. The change, there is a mistake here on this slide. This is a strong base, so it is a one-way arrow. The change in the concentration of all the species can be represented as follows. Again, in your ICE table, it is, again, you notice how in these acid-base equilibrium problems, it actually turns into initial change and final, but we still call them ICE tables. The reaction, the barium hydroxide initial concentration was 0.2 molar. The change, a strong base will totally ionize, so you lose it all, minus 0.02, so our final concentration is 0. Our barium has a 1-to-1 mole ratio with the barium hydroxide, so the gain would be plus 0.02. So your equilibrium concentration of barium ions are 0.02 molar. Your hydroxide, though, was a 2-to-1 mole ratio with your barium hydroxide. So it was 2 times that 0.02 to be 0.04. And so your final concentration of the barium hydroxide is 0.04. Now, on slide 35, that's hydroxide ion concentration. And let's remember, all these calculations, what we really needed was pH. So we go back to our equations and first calculate hydroxide ion concentration back into POH. So POH is minus the log of the hydroxide ion concentration, and that's 1.4. Therefore, from equation 1610, take your 14 minus your POH of 1.4, and your pH now is 12.60. Note that in both A and B, you have neglected the contribution of the autoionization of water, the hydronium and hydroxide ion concentration, because let's remember, that number is 1 times 10 to the minus 7th, which is so infinitesimal compared with 1 times 10 to the minus third molar and 0.04 molar. On slide 36, let's look at example 16.7. Predict the direction of the following reaction in aqueous solution. We have our nitrous acid plus a cyanide ion will yield our HCN and NO2 1- ion. On slide 37, the problem is to determine whether at equilibrium the reaction will be shifted to the right, favoring HCN and NO2-, or to the left, favoring the HNO2 and the CN1-. Which of these two is a stronger acid and hence a stronger proton donor, HNO2 or HCN? Which of the two is the stronger base and therefore the stronger proton acceptor, the CN or the NO2 1-? Remember, the stronger the acid, the weaker the conjugate base. So on slide 38, the solution in table 16.2, we see that HNO2 is a stronger acid than HCN. Thus, CN1- is the stronger base than the NO2 1-. The net reaction will proceed from left to right as written because the HNO2 is a better proton donor than the HCN. And the CN1- is a better proton acceptor than the NO2 1-. On slide 39, weak acids and acid ionization constants. A weak acid, what will happen with a weak acid is you will have HA. What is that? The hydrogen ion and then whatever your anion is. Plus water will give us our hydronium ions and our A- minus, our anion, and it will have a negative charge. So remember, we can drop the water out, and so HA, if it's a weak acid, we have the double arrows, is going to be the concentration of your hydronium ion plus times the concentration of our anion divided then by our HA. Again, this is called the Ka, and so Ka is an acid ionization constant. Now, as Ka increases, what that means then is that your weak acid strength is increasing. The weak acid strength would be increasing as your Ka gets bigger. So on slide 40, let's look at on table 16.3, the ionization constant of some weak acids and their conjugate bases. You knew from the beginning here, hydrofluoric acid is a very weak acid, Its Ka is 7 times 10 to the minus 4th. Whenever you're thinking about this, remember that would be 0.0007 is its Ka, is what you're looking at here. So realize what we're saying, these Kas are relatively low. Nitrous acid is listed. Aspirin here, the acetyl salicylic acid is 3 times 10 to the minus 4th. Formic acid, again, something in bee stings, is 1 times 10 to the minus 4th. Acetic acid, your vinegar, a component of vinegar, is 1.8 times 10 to the minus 5th. Reason I'd like you to remember that is most of your problems involve acetic acid because it is so common. Your conjugate bases, if you can have a Ka for a weak acid, you can have a Kb for a weak base. So your fluoride ion, Kb, 1.4 times 10 to the minus 11th. And again, there it is with its conjugate acid. So realize here that these are these Kb values. Again, peeking down at the bottom, we should keep track of the acetate ion because it comes up in many equilibrium problems. And then the cyanide ion, 2 times 10 to the minus 5th. Just so you realize where we're getting some of these numbers as we do our calculations is this table. So on slide 41, solving a weak acid ionization problem. Here's your job. Identify the major species that affect the pH. In most cases, ignore the autoionization of water and ignore hydroxide ion concentration because it is determined by the hydronium ion concentration. Use your ICE or ICF tables to express the equilibrium concentrations in terms of a single unknown X. Write Ka in terms of an equilibrium concentration. Solve for X by the approximation method. If the approximation is not valid, solve for X exactly. Calculate the concentration of all species and/or pH of the solution. So on slide 42, let's do example 16.8. Calculate the pH of 0.036 molar nitrous acid in solution. So HNO2 will dissociate, and again, weak acid, so we have the two-way arrows, hydronium ion and our nitrous ion. Example 16.8 strategy on slide 43. Recall that a weak acid only partially ionizes in water. So when you're given your initial concentration of a weak acid and asked to calculate the pH of the solution at equilibrium, you may want to make these sketches to try to keep track of the info that was given. They told us that the HNO2 initial, the little o is the initial again, was 0.036 molar. Okay? So your job is when you understand that the hydrogen ion and the NO2 ion are in solution, that being a weak acid, they're going to constantly reform back to the HNO2. And remember to ignore water's autoionization because it is a major source. So the only source of hydrogen ions is in the acid. The concentration, again, of the OH is 1 times 10 to the minus 7th if you're at room temp. So again, you can consider it a minor species. So on slide 44 then, the solution, follow the procedure outlined, and that is, look at the species that affect the pH of the solution. It's going to be the HNO2, the H+, and then the NO2, the conjugate base. So when we write our reaction, these are the species involved. We ignored water's contribution. Now, set X to be the equilibrium concentration of H plus and NO2, 1 minus ions in solution. X, and again, it was a 1 to 1 mole ratio with your weak acid, so that is why it is a plus 1X and plus 1X for your NO2. And then does it make sense that it's minus X for the HNO2? This is not like your strong acid. This is not dissociating 100%. So only a partial amount is going to be dissociated. So now your equilibrium expression becomes 0.036 minus X for HNO2. The hydronium and the NO2 ion are both plus 1X. And slide 45 then, step 3. From table 16.3, write the Ka, which you know is the product, concentration of the products raised to the power of their coefficients divided by the concentration of the reactant. Ka from the table was 4.5 times 10 to the minus 4th is equal to, if these were each x, that means we have x squared. And remember from our table, that equilibrium line, it was 0.036 minus x for our HNO2 concentration. Applying the approximation that 0.036 minus x is 0.036, right? Isn't that approximately the same? There's very little would subtract. Then what you can say is 0.4, let's just substitute in here that 4.5 times 10 to the minus 4th was Ka, x squared is our hydronium and NO2 concentration. And then this 0.036 is all we need in our denominator. So now let's do our algebra. Okay? Let us solve now for our x. Remember to multiply both sides by the 0.036, and you will then get x squared is equal to 1.62 times 10 to the minus 5th. Take the square root of that. 4 times 10 to the minus 3rd molar is the concentration at equilibrium. Now again, you can test this approximation. Was it okay to drop the x from the expression? We'll take the 4 times 10 to the minus 3rd and divide by 0.036, that initial concentration times 100. That's 11%. We're only supposed to have greater, we only want less than 5% approximation. So you cannot finish these problems that easily. We wanted to give it a shot that you would just ignore the x, but you cannot. Therefore, we need the quadratic equation again. And so when you do this, when you take our expression and back to this page, when you actually have then 0.036 minus x times 4.5 times 10 to the minus 4th is equal to x squared, and then set that all equal to 0, back to our quadratic expression, that would be x squared plus 4.5 times 10 to the minus 4th x minus 1.62 times 10 to the minus 5th is all equal to 0. So trying to solve for x, you have two possible, when you substitute in your a, b, and c in your quadratic equation, you would get your two values for x, 3 times 10 to the minus 3rd, or minus 4.3 times 10 to the minus 3rd molar. There's always two possibilities for x with the quadratic equation because of the plus minus of the square root. On 47 then, the second solution is physically impossible, meaning you cannot have a concentration of ions produced as a result of ionization to be negative. So you drop the negative number. And so now x is 3.8 times 10 to the minus 3rd molar. You're not done yet. Okay, what this problem wanted then was, what is the pH? That again, x you assign to be the hydronium ions concentration, so 3.8 times 10 to the minus 3rd. So pH is equal to minus the log of 3.8 times 10 to the minus 3rd, which again then would be 2.42 in your calculator. Let's check. Note that the calculated pH indicates that the solution is acidic, which is what we would expect for a weak acid. Compare the calculated pH with that of 0.036 molar. strong solutions, such as HCl, to convince yourself that there is a large difference between a strong and weak acid. Example 16.9 on slide 48. The pH of a 10th molar solution of formic acid, our HCOOH, is 2.39. What's Ka? So now they give us the concentration, they give us a pH, and we want to calculate the Ka. Our strategy, well, formic acid is a weak acid, therefore it only partially ionizes in water. Note the concentration of formic acid refers to the initial concentration. The 0.1 was your initial concentration before you started your ionization. The pH of the solution, on the other hand, was going to be, the pH is at equilibrium. So to calculate Ka, first what you need to do is the concentrations of the hydronium ion, the HCO1 minus ion, and the HCOOH at equilibrium. As usual, ignore the autoionization of water, and this sketch again. Might be helpful to list your variables. A formic acid, initially, this is your initial conditions, 0.10. It will ionize into hydronium ions and HCO minus. However, being a weak acid, you will still have some HCOOH. So at equilibrium, the pH again, at equilibrium, 2.39. Now, what would that hydronium ion concentration be, or hydrogen ion? On your calculator, take 10 to the minus 2.39, and you can calculate then the hydronium ion concentration. So in slide 50, we proceed as follows. Again, you identified the major species, formic acid, hydronium, and your conjugate base. Step 2, calculate the hydrogen ion concentration. And again, we already said to do this. And so taking the antilog of 2.39, 10 to the minus 2.39, you should, on your calculator, get 4.1 times 10 to the minus third molar. So in slide 51, summarize these changes then. So again, this is at equilibrium. So here's your formic acid was 0.1. We said that the hydronium ion concentration is 4.1 times 10 to the minus third from our pH number. Initially, the concentration was 0, but we need that 4.1 times 10 to the minus third because being a 1-to-1 mole ratio back up in our equation, that's how much acetic acid will dissociate, or formic acid will dissociate, minus 4.1 times 10 to the minus third. So you see this pH at equilibrium gave us the hydronium ion concentration. Since there's a 1-to-1 mole ratio, that is how much formic acid we lost, which is a number you can calculate, 0.1 minus 4.1 times 10 to the minus third. We're just showing you how you get it here. The hydronium ion concentration, again, the pH said it was 4.1 times 10 to the minus third, and since it's a 1-to-1 mole ratio with HCO minus, it's 4.1 times 10 to the minus third. Again, note that because the pH, aka the hydronium ion concentration, is known, we can know the concentrations of both the formic acid and the HCO minus at equilibrium. Slide 52 then on step 3. Write your Ka expression. Ka is equal to the concentration of the products raised to the power of their coefficients over the concentration of the reactant, and substitute the values in. We again, the pH told us, take the antilog, and so you get the pH, the hydronium ion concentration to be 4.1 times 10 to the minus third, 4.1 times 10 to the minus third for HCO minus. And then our acetic acid, remember to take 0.1 minus your 4.1 times 10 to the minus third. On your calculator, I hope you get 1.8 times 10 to the minus fourth. Now, we could have cheated and just looked back on table 16.3. If you remember, I pointed out formic acid's Ka and check. Well, the value is slightly different, but we rounded off a bit more in our calculation. On slide 53 then, percent ionization. Percent of anything is always the part over the total times 100. Percent ionization then would be the ionized acid concentration at equilibrium divided by the initial concentration, the total amount of acid. So how much ionized acid? That's your part over your total initial concentration. For a monoprotic acid, percent ionization for HA would just be the hydronium. If we want the percent ionization, would be the hydronium ion concentration over the initial concentration times 100. HA, again, with the sub O is initial concentration. Percent ionization. For a strong acid, it's 100%. That's why you get the flat line. But for a weak acid, we get this negatively sloped curve, and that is a weak acid's percent ionization would look like. On slide 54, let's look at table 16.4, which has the ionization constant of some diprotic acids and polyprotic acids, and then their conjugate bases. The one we'll be working with a lot is sulfuric acid, H2SO4, which notice here the Ka is huge. That means it's a strong acid and goes completely to its hydronium and sulfate ions. Well, once you lose that first hydrogen ion, then you're left with the hydrogen sulfate ion, and that too can be an acid. Notice up here that it actually was the conjugate base of sulfuric, but now in our second ionization, it will become the acid. So you can do the Ka for this. It's 1.3 times 10 to the minus second, which will lead you to your sulfate ion. Peeking down on the bottom, or you can just realize that all these Ka values are here and Kb values for the conjugate base. We're going to need these as in one of our labs that's coming up when we are working with phosphoric acid. The first phosphoric acid has a Ka you're going to try to establish to be 7.5 times 10 to the minus third. Then when it ionizes off one hydrogen, it will turn into H2PO4, 1 minus that dihydrogen phosphate ion. Then where you have one less hydrogen and one more negative charge. Now lose another hydrogen and you will become the hydrogen phosphate ion. The Ka2 we call this. This would be Ka1. This is our Ka2 is 6.2 times 10 to the minus 8. When we lose our last hydrogen and just isolate the phosphate ion, the Ka for this is 4.8 times 10 to the minus 13. On slide 55 then, with those diprotic and triprotic acids, what you saw is that you're going to yield more than one hydrogen ion per molecule. You're going to ionize in a stepwise manner, lose one proton, which is a hydrogen ion, a hydrogen at a time. And the ionization constant expression can be written for each of these ionization stages. Consequently, two or more equilibrium constant expressions must often be used to calculate the concentrations of the species in the final acid solution. With carbonic acid, when you lose the first hydrogen, you will have the hydrogen carbonate ion, and we call that Ka. Now, how will you calculate Ka? You'll take the concentration of the hydronium ion raised to the power of its coefficients times the concentration of the hydrogen carbonate ion divided by the carbonic acid's concentration. Now, this is just like our Hess's law. That product becomes our reactant. The HCO3 will ionize off another hydrogen stepwise here to end up with the carbonate ion. And so our Ka2 will be the hydrogen ion concentration times the carbonate ion concentration divided by the hydrogen carbonate ions concentration. On slide 56, table 16.5 has some ionization constant of some weak bases and their conjugate acids at 25 Celsius. We'll do some problems with ethylamine, so C2H5NH2 and Kb, because this is a base we have here. You can see how it will become a hydrogen ion acceptor when you turn into its conjugate acid. So the Kb is 5.6 times 10 to the minus fourth. The Ka for this conjugate acid, 1.8 times 10 to the minus 11. realize on this chart is where we're going to get these Ka and Kb values. On slide 57, oxalic acid, H2C2O4, is a poisonous substance used chiefly as a bleaching agent and cleansing agent, for example, to remove bathtub rings. Calculate the concentration of all the species present at equilibrium in a 10th molar solution. Our strategy on slide 58, determine the equilibrium concentrations of the species of diprotic acid in aqueous solution, is more involved than for a monoprotic acid. We follow the same procedures that used for a monoprotic acid for each stage. As in example 16.8, note the conjugate base from the first stage becomes the acid for the second stage ionization. So on slide 59, solution, we proceed according to the following steps. Step 1, the major species in solution in this stage are the non-ionized acid, then the hydrogen ions that's lost, and our conjugate base, the HC2O41-. Step 2, let X be the equilibrium concentration of our two products, the hydrogen ion and the HC2O41-. So at the initial concentrations then are summarized in our ICE table. We have our 10th molar H2C2O4 with the hydrogen ion concentration initially is 0. The change then, since it's a 1-to-1 mole ratio, will be minus X for our acid plus X for our hydronium and HC2O41- ion. So summing up this column, 0.1 minus X will be our equilibrium concentration of our non-ionized acid. X and plus X will be our concentrations of our two products. Do the Ka, which was given to us in the chart from table 16.4 then for step 3. And again, hydrogen ion concentration, our conjugate base there, and our acids concentration. We said that each of those were X, so X squared divided by, we said our concentration of our acid was 0.1 minus X. Let's see if we can use this approximation and assume that 0.1 minus X is that this is negligible and we can just use 0.1. Well, when we do, then this expression 0.1 minus X will just come down to be 0.1. So we can have then X squared is equal to 6. Well, first multiply both sides by 0.1. Then that would leave X squared to be 6.5 times 10 to the minus third. And solving for the square root, you get 8 times 10 to the minus second molar. On slide 61, is that valid? No. When we take 0.8, or we take 8 times 10 to the minus second divided by our 0.1 times 100, that's an 81% estimation or approximation. That is not valid. So that means we must use the quadratic expression. And remember, when you had your expression, what you now have is X squared plus 6.5 times 10 to the minus second X minus 6.5 times 10 to the minus third. Set that all equal to 0, plug it into your calculator, solve for A, B, and C, and X comes out to be 0.054 molar. On slide 62 then, step 4, when the equilibrium, this was for the first stage of ionization. So these concentrations mean hydronium ion is 0.054. Our conjugate base, 0.054 also because it was X, and our acid was 0.1 minus that 0.054, which is 0.0546 molar. Now, consider the second stage of ionization, meaning when our HC2O41- will ionize to our hydrogen ions and then our oxalate ion. At this stage, the major species again is the HC2O41-, which now becomes the acid in the second stage of ionization, and then the hydrogen and the oxalate are oxalate will be our conjugate base. On slide 63 then, step 2, letting Y, you can still call it X if you'd like, but if you want to call now Y, just so that you understand it's in the second stage of ionization, Y would be the equilibrium concentration of the hydronium and the oxalate ion. Then that would be how much is lost from our HC2O41 minus. So initial, we calculated in part 1, was 0.054 molar for HCO2. We said minus Y because it's a 1-to-1 mole ratio. So our equilibrium concentration in our ICE table for HC2O41 minus is 0.054 minus Y. We had, remember, you calculated these to be, the hydronium ion concentration was 0.054. So when you summarize in the ICE table the concentration of hydronium, it's 0.054 plus Y. You didn't have any oxalate ion, so the amount of oxalate present in this second ionization will just be Y. Step 3 then, from table 16.4, we get the Ka for our HC2O41 minus, and it's equal to the hydronium times the oxalate ion concentrations divided by our acid. So substituting our equilibrium values into this Ka expression, you can solve here, and you will get 0.054 times Y, and again, making the assumption that 0.054 minus X will be negligible. You're going to get your Y, or your equilibrium concentration, to be 6.1 times 10 to the minus 5th molar. Testing that approximation, 0.11%, much less than 5, so you could do this as you solve this problem, drop that minus Y there. So step 4 then, on slide 65, at equilibrium then, what this says is the H2C2O4, it was 0.046 molar. Our HC2O41 minus was the conjugate base, which became our acid in the second ionization, was 0.054. You said minus Y, so that would be 0.054. Hydronium ion, you're going to add the 6 times 10 to the minus 5th that you calculated. It still comes out to be 0.054. The oxalate ions concentration, then we said, was Y, so it's 6.1 times 10 to the minus 5th molar. So hydroxide ion concentration then is going to be, we need to use our Kw, which was going to be the hydronium times the hydroxide ion concentration. And so Kw is 1 times 10 to the minus 14. And so that's going to be equal to the hydroxide ion concentration divided by the 0.054. So when you substitute in the 0.054 for the hydronium ion concentration, hydroxide ion concentration is 1.9 times 10 to the minus 13th mole.
Base ionization. This animation demonstrates the difference in ionization between a strong base, sodium hydroxide, and a weak base, ammonia. Click on one of the buttons to view sodium hydroxide, NaOH, or ammonia, NH3, dissolving in water. Sodium hydroxide dissolved in water is a strong base. Strong bases are strong electrolytes. For most purposes, strong bases ionize completely in water and produce a significant number of hydroxide ions. The Arrhenius definition of a base is a substance that ionizes in water to produce hydroxide ions. The Bronsted definition of a base is a substance that accepts protons or hydrogen ions, H+. Hydroxide is the strongest base that can exist in water. Hydroxide ions will readily accept hydrogen ions from an added acid to produce water. Hydroxide ions plus hydrogen ions yields water. Ammonia, NH3, dissolved in water, is a weak base. Weak bases are weak electrolytes, which only ionize to a limited extent in water. At equilibrium, an aqueous solution of ammonia contains mostly non-ionized ammonia molecules and a small amount of ammonium ions, NH4+, and hydroxide ions, OH-. Given equal concentrations of an ammonia solution and a sodium hydroxide solution, the weak base, ammonia, will produce a much lower concentration of hydroxide ions than the strong base, sodium hydroxide. Note that water molecules surrounding or hydrating each of the ions or molecules in solution were not shown in this animation. The main focus of this animation is to show the transfer of a hydrogen ion from water to ammonia.
On slide 66, let's talk about weak bases and base ionization constants. A weak base example is ammonia. Ammonia, when you put it in water, will undergo a reaction to make your ammonium ion and your hydroxide ion. This is obviously a weak base situation. And so what we do is we will, in order to calculate a Kb, we do just what we did with Kas. It's the concentration of the products raised to the power of their coefficients divided by the concentration of the reactant raised to the power of their coefficient. Notice how we left water out again. Kb then is what we call the base ionization constant, and we've seen that in a couple of our tables already for what Kb values can be. And what we know is that if Kb goes up, that means that you have a weak base. As Kb gets greater, that is actually indicating a weak base, that there's for the dissociation. Solve weak base problems like weak acid problems, except solve for hydroxide ions instead of hydrogen ions. Example then, 1611 on slide 67, what's the pH of a 0.4 molar ammonia solution? Our strategy on slide 68 then, the procedure here is similar to the one used for a weak acid. We just did that in example 16.8. First, from the ionization of ammonia, we see that the major species in solution are the ammonia, the ammonium ion, and the hydroxide ion. And again, it's always good to maybe have a picture of that from our reaction, is that the ammonia and the water made the ammonium ion and hydroxide. The hydrogen ion concentration is very small, as we would expect from a basic solution, so it's present as a minor species. As before, ignore the ionization of water, and we again make a sketch. And as we said, ignore this slight amount of hydrogen ion that's made. On slide 69, our solution then, step one, the major species again were ammonia, ammonium, and the hydroxide ion. We ignore the very small contribution to hydroxide ion concentration of water. So here's your reaction. Line 1 of your ICE table is going to be ammonia plus the water we're going to ignore, so you don't even need it, yields the ammonium ion and hydroxide. We had said the initial ammonia concentration was 0.4. The change is going to be minus X, so the equilibrium concentration of ammonia would be 0.4 minus X. Ammonium is originally, there was none, nor did you have any hydroxide. So X then is the equilibrium concentration of your ammonium ion and your hydroxide ions. And so equilibrium would just be X for both of those because they are a 1-to-1 mole ratio. On slide 70 then, Kb is calculated by taking the product, the concentration of the products raised to their power of their coefficients times the concentration of the reactants. Kb was in the chart for ammonia, 1.8 times 10 to the minus fifth. We assigned x squared, and so this then is 0.40 minus x. Apply the approximation, can we, of just ignoring x, What we will then have to solve for is 1.8 times 10 to the minus fifth is equal to x squared divided by 40. X squared, then multiplying both sides by 40, then taking the square root of x, taking the square root of 7.2 times 10 to the minus 6, we get x to be 2.7 times 10 to the minus third molar. On slide 71, check your approximation. Was that okay that we dropped the x? This is how you do it. Take the answer divided by that initial molarity, and 0.68 is much, much less than 5, so the approximation is valid. So next, what you say then is that gave us our hydroxide ion concentration was 2.7 times 10 to the minus third molar. Remember, hydroxide can be converted to POH by using this equation. POH is equal to minus the log of your hydroxide ion concentration. That would be 2.57. So what the question was, what was the pH? What we do then is take 14 minus this 2.57, and we have 11.43 is the pH. Check here on slide 72. Note that the pH calculated is basic, which is what you would expect from a weak base solution. Compare the calculated pH with that of a 0.4 molar strong base solution, such as KOH, to convince yourself of the difference between the strong and weak base. On slide 73, let's look at ionization constant of conjugate acid-base pairs. Let's remember, a weak acid consists of a hydrogen ion attached to an anion. And when it undergoes ionization, you're going to get hydrogen ions in your anion, A minus. So Ka is going to, that would be your Ka1. Now, take this weak, take your weak anion and add it to water, and what you will happen is that you will get your Kb value. Your anion, this base that was formed here, is going to react with water, and you will get your hydroxide ion, and you will recover your acid, and that will be determined by a Kb. When you add these up, these two equations, and cross out like species, what you will end up with then is water, bring down what you didn't cross out, plus hydrogen ions. Water will dissociate and give us hydrogen ions and hydroxide ions. And that, as we recall, is Kw. Therefore, a new equation we can use is Kw is equal to Ka times Kb. Weak acid and its conjugate base on slide 73 on the bottom then says, let's rearrange this equation. What if I want to solve for Ka? We'll take Kw divided by Kb. What if I want to solve for Kb? Take Kw and divide by Ka. On slide 74, what we need to keep track of is that molecular structure and how that's going to be linked to acid strength. The molecular structure is, again, of an acid would be a hydrogen ion connected to some anion. X could be the appropriate symbol for any anion. If it's a strong acid, it will just completely dissociate into your hydrogen ion and your X. So the stronger the bond, the weaker the acid then. The stronger it stays together. So here we go with our acid strength. We know here that hydrofluoric acid is a very weak acid. And that's what we're trying to get you to see here, is that hydrofluoric is very, very weak compared to hydrochloric, hydrobromic, or hydriodic